everybody. Let's do a quick recap of what we did last time about polar graphs, and then you can practice a little bit, stretch your thinking with a couple of practice problems. And then after this quick recap, I want to show you a truly beautiful result. It's the one that I've been promising that connects complex numbers in the complex plane to trig identities. Okay, so let's jump in. You remember the difference between rectangular and polar coordinates. Rectangular coordinates tell you how far over, how far up. Polar coordinates tell you the angle that you are pointing in and the direction along that heading that you have to travel to get to a point. So you can also, as we said last time, make rectangular and polar graphs with equations that relate those two quantities. So when you're making rectangular graphs, like way back in Algebra 1 when you did this, you consider x to be your independent variable, and so you can range over several different values for x. And then for each one of those, you plug it in, and that gives you a corresponding value for y. And then you can plug those in, or rather you can plot them to get a graph. So similarly, here we're trying to figure out r as a function of theta. So theta, the angle, would be our independent variable, and r would be the dependent one. So again, you can range over values of theta, only it would be nice to choose values of theta that are kind of easy to think about. So if I'm imagining graphing these, you could choose some regular increments. So you could choose increments of 45 degrees. You could choose increments of 30 degrees, so 30, 60, 90, like that. But because all of the mathematical world works in radians, let's think in radians. So here I've plugged in increments of 30 degrees, so pi over 6, pi over 3, pi over 2 is straight up, then 2 pi over 3, then 5 pi over 6, and then pi, and you can continue to go around. And if you put the values for r under a common denominator, you can see that we're increasing by 1 pi every time. So what we end up getting if you plot this is when the angle is 0, so when I'm pointing that way, the radius is 0, which is the origin. Then when I'm pointing at an angle of pi over 6, I go a distance of pi over 18. So I'm imagining that distance is pi over 18. And then when I'm at an angle of pi over 3, this direction, I go 2 times pi over 18. So this distance is twice that distance. As usual, my pictures may not be wholly accurate. And what you end up getting if you plot all of this is this kind of spiral shape. Let's pause for a second to think about a question that you may not have considered yet, which is how do you deal with negative values? In rectangular coordinates, a negative x value would mean that you go to the left instead of to the right. But what would a negative value mean? Well, and you know how to deal with a negative angle. You know that positive angles wrap in this direction, so a negative angle would involve wrapping in the other direction. But what about a negative distance? In particular, where would the point -2 at an angle of 45 be? Let me show you by referencing this point first. So here, if I'm at an angle of 45 degrees and I travel a distance of 1, that's approximately here. I wouldn't quite get to this point out there because that distance is square root 2. So this is about where this point A would end up. So what happens if I'm pointing at the same angle of 45 degrees, but the distance isn't 1, the distance is -2? The answer is you would go in the opposite direction. So you can think about it as you have a number line going out this way in the direction that your angle's pointing. So this would be a distance of 1 along that line. This would be a distance of 2 along that line. This would be a distance of 3 along the line. So if I want to go a distance of -2, I would just go 2 units in the opposite direction. So if this is point B, it would end up over here. So using that idea now, let's make one more plot. So what would a polar plot of r equals cosine theta look like? You know the rectangular plot of y equals cosine x. It's that one. So now let's think for a second about this other one. All right, let's evaluate this one at all the multiples of 45 degrees. So pi over 4, pi over 2, 3 pi over 4, and so on. And I've sort of made little dotted lines to indicate where those angles are. Plug it in. All right, there we go. I made a little unit circle here. Remember, cosine of an angle is telling us the x-coordinate of the point on the unit circle at that angle. So when you start at an angle of 0, the cosine value is 1, because the point's out here. As we rotate, the cosine value is decreasing towards 0. So we start with an x value of 1, decreasing towards an x value of 0. Then we continue to decrease from 0 toward -1, then from -1 back to 0, and so on. So let's plot that here. When we're at an angle of 0, let's put 1 way out here. All right, so I've plotted that point. Let's plot pi over 4 at a distance of root 2 over 2, so that's this way. So I know, let's actually trace out what the unit circle would be here, just to give some sense of scale. Okay, so at pi over 4, I'm not going to be out there, because that would be a distance of 1 in the direction pi over 4. Root 2 over 2 is smaller than that, so let's put it about there. And then once I'm facing upward, the distance is 0. So if you were going to imagine filling in some intermediate angles, the intermediate angles are going to... Whoa. Okay, this is a terrible sketch. We'll do it in Desmos in a second. But at intermediate angles, you're going to get distances that connect them with a smooth curve. So when the angle is here, you're at a distance of 1, and then as your angle smoothly rotates this direction, the distance along that line is also decreasing. And so if you imagine both of those motions happening at the same time, you end up with a shape like that. Okay, what happens as we face this direction? So as we move from facing up to facing that direction, the distances become negative. So instead of having points that move out in this direction into quadrant 2, because those would be positive distances for the angle we're facing at, we have negative distances for the angle we're facing at. So we would end up actually plotting over here in quadrant 4. So a distance of root 2 over 2 in this direction would actually end up over here. And then a distance of 1 in this direction would be out here. So a distance of -1 in this direction would actually be back here. And so we end up right back where we came from here. 5 pi over 4 is facing this way. So a negative distance for 5 pi over 4 would actually take us the other direction. And notice that we are going a distance of negative root 2 over 2, and that's the same as the root 2 over 2 for this direction. So when we were headed at 45 degrees, we went root 2 over 2. When we're headed this direction, we go negative root 2 over 2, which is that same distance in the same direction. So this point right here overlaps that point right there. It's the same point. It's right here. So if you're pausing thinking like, oh, wait a minute, what just happened? Pause the video. Go back and think this through really carefully. You can get it, but it takes reconstruct it for yourself. Think step by step, what direction, what distance, and reconstruct the picture. So at 3 pi over 2, when we're facing down, we've got a distance of 0, so that's this point again. When we're facing this direction, now we're at a positive distance of root 2 over 2, which is exactly this point. So this point has overlapped which? This one. These two have overlapped each other. And then at an angle of 2 pi, we go a distance of 1, which is here. And so this point has overlapped that point. So it seems to have made this shape. Let's take a peek in Desmos. So you can double check all your polar thinking here by saying r equals cosine and then just type the word theta. And so you can see that my sketch wasn't very good because r cosine theta actually makes a circle. Don't get confused with vague thinking here. You know that sine and cosine both have to do with the unit circle, which is a radius 1 circle centered at the origin. But this circle is different than that. It's not radius 1. Its radius is half. And it's not centered at the origin. It's centered over here. So it's quite a different kind of thing, although obviously they're interrelated. So you might want to kind of go backwards and think a little bit about why did this end up centered here? Why does it have the radius it has? let me show you something surprising that you can investigate in the problem set. What if instead of cosine theta, we have cosine 2 theta? Oh, now it's made this very pleasant cloverleaf. So it's worthwhile thinking about why does the cloverleaf happen when we make this 2 theta. And then here's 3 theta. Here's 4 theta. So there's a lot of interesting questions you might pose for yourself here. And hopefully you could pose some questions and answer them. That's like what truly doing mathematics would be about. But I've also posed some questions for you in the problem set. All right, enough review. Let's turn to topic number 2, which is beautiful proof. Okay, so quick recap of what we know about this. Here's the complex plane. I've got 2 complex numbers. I told you a geometric rule for multiplying them. So if we're going to have a new complex value c, that's a times b, I said that the way that you can find c is based on a polar way of thinking about the complex numbers. So you can define angle A would be this angle, the angle that you were pointing at to get to the complex value A. And the angle B would be, here, let's do them in different colors. So let's make angle A be blue, and let's make angle B be pink. So the rule that I told you was the angle that you have to travel in to get to point C is angle A plus angle B. And the distance that you have to go to get to C equals the distance you go to get to A times the distance you go to get to B. Whoops, there we go. And I'm not proving this for you, but you could prove it. And for now, I want to use this important idea. So if I wanted to know where C was here, for example, I'd take that blue arc, put it on top of the purple arc. So that would be pointing in a direction, more or less this way. The question is, how far do I go in this direction to get to point C? And the answer is this distance times that distance, which is, who knows, somewhere up here. Okay, so that's not how we're going to use it, though. We're going to use it to prove trig identities. Okay, so quick warm-up. Let's say this is the unit circle on the complex plane. So this is 1, this is I up here. All the points on this circle are distance 1 from the origin. So let's consider points A and B. Point A is the complex number root 2 over 2 plus root 2 over 2i. Complex number B is negative root 2 over 2 plus root 2 over 2i. What happens if we multiply them together? Like, obviously, you could just multiply them. And, that might feel a bit messy. Don't multiply them. Instead, use the rule. What's the rule? To find where C lands, add the angles, multiply the distances. So pause the video, think, where should it end up? All right, let's think about the angle first. So if I add these 2 angles together, this is 45 degrees here. So if I add 45 degrees to this angle, that's like putting it here. So I should have 180 degrees as the resulting angle. So what I know is point C is located in a direction that's an angle of 180 degrees. So it's out that direction somewhere. So the next question is, how far do I have to go to get to point C? Let's think about distances. What is this distance to the point A? Oh, well, I put it on this unit circle, so it's got a distance of 1. The distance to the point B is also 1, so 1 times 1 is just 1. So I know that the distance I need to travel in this direction is a distance of 1, so here's where C ends up. So what I know without even multiplying this out is that C equals negative 1, and I've done that just geometrically. If you're thinking that that feels like a weird magic trick, go ahead, multiply this out, and you'll see that it actually evaluates to be negative 1. Actually, here, I'll just do it for you. Well, no, I'm not going to do it for you. It's a bad teacher. You do it. But actually, do it a different time, because let's now proceed to the main show. All right, so let's do this identity. I want to prove that cosine 2 theta is cosine squared theta minus sine squared theta. And we'll think about sort of why that makes sense using complex numbers. So let's think about a complex number A that's somewhere on this unit circle. So you could write A in terms of its real part and its an imaginary part. So you could write A like x plus y times I, where x is the real part and y is the coefficient for the imaginary part. But let's not write it using the rectangular way of writing it. Let's write it using the polar way of writing it. So let's call this angle theta, and let's call this distance, well, I guess we don't have to call it r, because since it's on the unit circle, the distance is 1. So let's write this as 1 times the angle theta. Not times, sorry, 1 in the direction of the angle theta. Okay, now that I'm drawing the picture, I think maybe let's switch goals, actually. Let's try and prove the double sine formula instead, because that's going to kind of fit the picture better. So if I want to show what sine 2 theta is, I already have this nice picture that's got a theta in it. How would I represent 2 theta in this picture? Well, it must be, like if this is theta, let's just stack another theta right on top of it. And now that I've got both of those together, that is 2 thetas. All right, so here I've got this mystery point up here that's some complex number. But I know that the angle to the complex number is 2 theta. So here's going to be our strategy. Think about this tall pink line. We're going to describe the length of this pink line in 2 different ways. Here's the first way. Let's think about SOHCAHTOA on this triangle, all right? What we know about SOHCAHTOA of this triangle is the length of this pink line, there, equals, what is it? So SOHCAHTOA says sine of 2 theta equals pink line divided by 1. So what that means is that the length of the pink line is just equal to sine 2 theta. Great. So let's describe that same height in another way. You know that if I was going to write the coordinates of this point using rectangular coordinates for the complex number, the distance over would be the real part and the distance up would be the imaginary part. So for example, like let's pretend it's not true, but let's pretend this point is at like, root 2 over 2 plus root 2 over 2i. So that would mean that the height of the pink was this root 2 over 2i, because that's telling me how many units I go in the imaginary direction. Okay, so let's try and figure out what exact number does this represent. And now is where we can use the trick. We know that the point A is here at an angle theta. Remember that when you multiply complex numbers, their angles add. So think for a second about where would A times A end up. Let's see. A times A would be the angle to A plus the angle to A. So that would be like theta plus another theta. So what we found is that this number right here is actually the number A squared. That's it. So let's write down A using rectangular coordinates, and then let's actually square it. So if I'm looking at the point A here, because the angle's theta, if I think about what would the sine of theta be? Sine theta would be this line, the length of this line divided by 1. So what that tells me is that the imaginary part has a height of sine theta, and so that's where the I sine theta comes from. This distance would be the cosine of theta divided by 1, which is just cosine theta. And notice that this is the real part of that number. It's how far over I go along the real axis. So if I wanted to write down the coordinates of this point in a rectangular way, I'd say cosine theta plus I times the sine of theta. All right, time to do the multiplication. So if I want to know what are the coordinates up here, what's the real part, what's the imaginary part, let's just multiply A times A. So let's see, A is cosine theta, I sine theta. A is cosine theta, I sine theta. Go ahead, pause the video, try and do the multiplication yourself and see what happens. Okay, fair warning, I'm going to do it. So cosine times cosine is going to give us cosine squared theta. Then cosine times I sine gives us I sine cosine theta. I sort of reorganized all the terms there. Then this one gives us another I sine times cosine. So I sine cosine. And then lastly, these two give us I squared sine squared, because each of the parts multiplies. Okay, how can we simplify this? Well, you guys know what I squared is. It's -1. So let's replace that with -1. And let's group together all of the things that are real numbers and all the things that are imaginary numbers. So it's only imaginary if it's got an I in it. So this is an imaginary part. This is an imaginary part. And I'm noticing that they're the same, right? So I've got 2 of them. So let's combine those together over here as 2i sine theta cosine theta. Here I've got cosine squared and minus and then a sine squared. If you're starting to get a tingly feeling, that is not out of place. Okay, so what have we done here? We've figured out what are the components of a squared? Like what is this number up here? If we knew what the angle was, we would plug in the numbers, and this would give us a single number that tells us how far over, what's the real part. And if we knew what our angle was, we would plug them in here. That would give us a single number that tells us how far up in the imaginary axis. So really, this is the same thing as any old numbers, like 2 plus 3i. It's just that the 2 is encoded in this complicated way. And also, it wouldn't be 2 plus 3 because then it wouldn't be on the unit circle. Okay, but what has this actually told us about our original question? Think about what this tells us about the length of this pink line. Stare at it for a minute. Stare at it until you start to feel really happy. So let's see. The length of this pink line must be the imaginary part of this number. I know that this gives us the coordinates of this number. Oh, here's the imaginary part. And usually when we write the imaginary part, if it was like 3i, the I is just telling us which direction we're going in. The 3 is telling us the distance we go in that direction. So let's actually kind of take the I out here. So I is telling us what direction we go in. 2 sine cosine is telling us the length of that line. And voila, you'll notice it's the right-hand side of this equation. And we also said that the distance of the pink line is also the same as sine 2 theta from SOHCAHTOA. So what this equation is really doing is it's showing us the length of this line in 2 different ways. On the left, as SOHCAHTOA applied to this triangle. On the right, as the imaginary component of this complex number. But because both sides of the equation describe the same length, we know that they must be the same. And you may have noticed that we got the other one for free. Cosine squared minus sine squared is telling us this distance here, which is the real part of the value a squared. If I was going to apply SOHCAHTOA to this big triangle, this distance would be cosine of 2 theta, because cosine 2 theta would be this distance divided by 1. So this value up here, the same calculation got us both of them. That is some pretty excellent math, if I do say so myself. I mean, obviously I didn't invent it, but it still feels so good to see it. So whenever you see a result, it's always worthwhile asking, could I take it one step further? So could you take it one step further? What if we were going to do this? What if we were going to add another theta on the end here? Think about what would this complex number be? How would you calculate its real part and imaginary part? And then how could you use that to derive your own equation for sine 3 theta cosine 3 theta? Only using complex multiplication. Good luck.